You guys an extra minute to do yours. So the first one here, y varies inversely with x. What does that tell us? Yeah, y gets smaller when x gets bigger, so y equals k over x. Y is 8 when x is 12. So y equals k over 12. We would multiply that by 12 to get that k equals 96. So y equals 96 over x. And then 96 over 16 is 6. So y would be 6. How many had 6 for the first one? Number 2. Y varies directly with the square of x, means y equals k times x squared. So y is 36 when x is 3. We do actually have to square it, so 36 equals k times 9. We divide by 9 to get k equals 4. So y equals 4 times x squared, and then which is 100. You guys have any questions on the variation stuff? Okay then. Well, so what's the first step up here for number 1? We're going to isolate. Okay, yes, we have to isolate the exponential, so we're going to subtract 8. So 4 times 5 to the power of 3x minus 7 equals 100, and then what? Divide by 4. So 5 to the power of 3x minus 7 equals 25. And then 5 to the power of, we reverse that by doing log base 5, right? So the log base 5 and 5 to the power of cancel out. We have 3x minus 7. What's log base 5 of 25? Remember, it's log of 25 divided by a log of 5. Should give us 2. And then so add 7. 3x equals 9. And then divide by 3. X equals 3. How many of you had x equals 3 before I gave you the answer? Okay. I knew where Josh was coming from, or Jordan was coming from there, sorry. Yeah, you were acting very Josh-like at that moment. Number 2 is a little bit simpler. What do we have to do here? Well, yeah, we have to get rid of that. We could divide that out and get 5, couldn't we? 5e to the negative t over 15,000.0008. And then yeah, we have to get the exponential by itself again, so we're going to divide by 5. So we got 0.6 equals e to the negative t over. Now, I'm going to just make this easier on myself and multiply out the 1,500 times 0.00008, which is 0.12. And then, let's go back here. What's next? What do you think, Jordan? Got to get rid of the e. How do we get rid of e? What's the inverse of e? ln. So the ln and the e cancel out. That is negative t over 0.12 ln of 0.6. negative 0.511. And now I'm going to multiply both sides by a negative 0.12. And we get 0.061 equals t. So in other words, 61 milliseconds. T is time, so it'd be seconds. What do you guys think? You look like you're in pain, Jordan. You okay? Okay. Just making sure. Well, and that formula there, remember, we actually looked at that formula a little bit yesterday. It is the current across the capacitor going through a circuit with a capacitor in it is equal to that maximum current, which is your voltage divided by resistance. That's the maximum current when the capacitor isn't showing any impedance, when the capacitor is at zero charge. Times e to the power of negative t over RC. RC here is something called a time constant. A time constant is the amount of time it takes to discharge 63% of the capacitor for that resistance. We represent the time constant with the Greek letter tau. Looks like that, kind of a funny looking script T. And for an RC circuit, tau, the time constant, is simply R times C. Now, that's for an RC circuit. An RL circuit, a resistor inductor circuit, our time constant is tau is, the inductance divided by the resistance, L over R. The time constant kind of serves almost like a half-life in our half-life formulas, if you remember that formula. We divide our time by that time constant to get that 63% point. So if we're looking at charging a capacitor, the voltage on that capacitor as we charge it, the voltage with a little c there, that's the voltage on the capacitor, is equal to big V, which is the voltage of the voltage source, times 1 minus e to the negative time over tau. Now this is a capacitor, so tau is what? RC, very good. The current, how would we find the current that is flowing into the capacitor? Any idea? There you go. It's the same formula, we just have V over R. Like that. Discharging a capacitor. So for discharging a capacitor, the voltage on the capacitor is equal to that maximum voltage, because if we fully charge the capacitor, that capacitor charges to the voltage of our voltage source. That's still our voltage source voltage. Times E So negative T over tau. Notice it's just not with the 1 minus anymore. And of course, the current is the formula we just did we solved for one of our equations. This here, this is while it's charging, this is while it's discharging. So we've already really done the formula similar to the charging, or to the discharging. Let's look at charging. Find the voltage on a capacitor. 30 milliseconds after closing the switch. Say closing the circuit. If the maximum voltage is 120 volts, the resistance is 2.5 kilo ohms, and the capacitance is, well, let's go 45 microfarads. So this formula for charging, this is charging it now. That voltage is 120 is the maximum voltage times 1 minus E to the negative 30 milliseconds is going to be 0.03, correct? So negative 0.03 over tau is R times C. So I'm going to put this in parentheses. That's going to be 2,500 times 0.000045, correct? Does that look right? So now all we have to do is throw this into the equation. So 120 times parentheses 1 minus, we do second ln to get e to the power of. Now in your calculators, you probably got to do parentheses negative 0.03 divided by another parentheses 2,500 times 0.12345, close parentheses, and then I got to close the bigger parentheses. So what I did is I had to add a set of parentheses like that around that whole exponent. So I do have to have two parentheses closing in my exponent and another one to close off the formula. I get 28.09, we'll call that. 28.09 volts at 30 milliseconds. Does that make sense? Here's a little bit more difficult question. At what time does it reach 80 volts? So it's the same question, only now we're putting 80 in for the voltage. And we are looking for the time. How do we solve this? We're going to divide by the 120. Very good. So what we have over here is 2/3 equals 1 minus e to the negative t. Now I probably don't need these big parentheses here anymore. Now this is the tricky part. I actually have to subtract 1. So it's going to be negative 1/3 equals negative e to the negative t over I'm just going to go ahead and multiply that 2,500 times 0.1125. Now what do you think I have to do next? You got it. Get rid of the negative. Multiply by -1, so positive 1/3 equals e to the blah, blah, blah. And then ln of 1/3, you got it. Gives us negative 1.099 equals, now that cancels out the e, so that's negative t over 0.1125. So now the last step to solve this, I am going to multiply by a negative 0.1125. That gets rid of the negative here and multiplies by the 0.1125 at the same time. So times negative 0.1125. We get 0.124. I go 0.1236 equals t. What that means is that is at 123.6 milliseconds that it reaches 80 volts. What do you think? Good stuff? Zura's just got that look of, I'm not going to say anything. I don't get it, but I don't want to say anything because you'll keep talking. Am I right? No? Let's look at an inductor. An inductor doesn't really store voltage. It stores current. So if we look at an inductor, while it is increasing current, you don't really call an inductor as charging, it's just building current. The amount of current in that inductor, IL. Now when it's increasing, it starts out at a high current and slowly, as it builds, it decreases. So it's your voltage over your resistance, that would be your maximum current flow, times 1 minus e to the negative t over tau. Decreasing current, current on the inductor, V over R times E to the negative T over tau. What is tau now in this case? L divided by R. Inductance divided by resistance is our time constant. L is just inductor, the inductance. So find the current. I'll put a note in here, increasing after 150 milliseconds if the voltage is 60 volts, resistance is 3 kilo ohms, and inductance is, trying to remember my reasonable, let's just go 200 henries. So increasing means we're using this formula right here. Our current in the inductor is going to be our voltage 60 over our resistance of 3,000 times 1 minus E to the power of negative 0.15. That's the negative 150 milliseconds. And now I have to put this in parentheses. It's going to be the 200 henries divided by 3,000 ohms, and close that up. So to punch this in, it's 60 divided by 3,000 times parentheses 1 minus second ln to get my e to the power of. Now I'm going to add a set of parentheses around my exponent again, just to make sure. So I have parentheses negative 0.15 divided by parentheses 200 divided by 3,000, close parentheses and close parentheses, get out of my power and then close parentheses again. Oh, what I do. Oops. There. I hit the minus sign instead of the negative sign. It gave me an error. So I get 0.0179. That is saying that it is 17.9 milliamps. What do you think? Now, you look at that, that looks like it's pretty small. But remember, we've got 60 volts and 3,000 ohms. 20 milliamps is our maximum current. So it's getting really close to the maximum current at that point. How about if I ask how long before the current reaches 10 milliamps? So we're still on an increasing current here. We have 10 milliamps, which we're going to put in as 0.01 amps equals 60 volts over 3,000 ohms times 1 minus e to the power of negative t divided by, what was it, 200 henries divided by 3,000 ohms. So now to solve this, I divide this out here and I can get 0.02, correct? Then what? Get rid of my 200s. So that becomes 0.5. I can get rid of my parentheses over here now, so it's 1 minus e, the negative t over 200 divided by 3,000. And then subtract 1, so this is now negative 0.5 equals negative e to the negative t over. And then, multiply by negative 1 to make them both positive. Now we have to, ln is correct. So over here we've got negative t over 200 divided by 3,000. ln of 0.5 should be a negative 0.693. We are going to multiply by a negative 200 over 3,000. So I'm going to take my 0.693 times a negative 200 divided by 3,000. I get 0.0462 equals T. That is saying it takes 46.2 milliseconds to get to the 10. Does that make sense? Okay, you guys have a packet. In your packet, page 481. 1 through 27, the odds. Deal with capacitors. Page 487, 1 through 27, the odds. Deal with inductors. Are those pages in your packet, or do you need a new one? Do we go that high? Yep. Okay.